Okay. So let's get started. So let me start where I stopped, which is at this main equation I was writing. So let me just recall a few things. So we are looking at a certain matrix integral, z of nv, which was integral dm e to the minus n trace v of m over a space I called H, which were just Hermitian n by n matrices. Okay. And we were considering a ratio z of nv divided by z of nv0, where basically for v I take an even polynomial. So let me be more specific. Let's write v of x is x squared over 2 minus sum g2k x to the 2k over 2k. Let's say from 2 to some upper bound, let's say d. Okay. So this particular choice of polynomial v was supposed to do for us the job of enumerating random maps of arbitrary genus, which was the minimal embedding genus of the corresponding map, and with vertices, okay, of various degrees, even degrees, and each vertex of degree 2k would receive a weight g2k. So this g2k is just a weight in the enumeration per vertex of degree 2k. And there was, of course, the simple example in which we would have only g4 equals g and all other g's equal to 0. And then that would be the case not of the quadrangulations, but of the tetravalent maps. But by obvious duality, these were as well the quadrangulations. Okay, so that's v of x, and now v0 is just the quadratic part. So it's like v at g equals 0, right? So v0 is just x squared over 2. So we had to compute this ratio because the logarithm of this ratio was precisely the generating function we were after. Okay, so with this technique of orthogonal polynomials applied to the calculation of this matrix integral, we ended up with basically a closed set of equations. So n over n was v prime of q pn minus 1 over pn minus 1 pn minus 1, with q being the operator if you want an operator which was interpreted in terms of random walks, acting on the basis of pn, acting like pn plus 1 plus rn pn minus 1. Rn being itself related to the norms of the orthogonal polynomials pn in this way, where hn is just pn, and the p's, I recall, are the monic orthogonal polynomial with respect to the one-dimensional measure d lambda e to the minus nv of lambda. Okay? So this is how things occurred. Of course, the data of Rn is almost that of all Hns, except that you have to know H0. But H0 is particularly simple because H0 is the norm of a unique monic polynomial of degree 0, which is 1. Okay? So the norm of 1, which is just the one-dimensional integral itself. Okay, so it's a one-dimensional integral. All right. So basically, knowing the Rns will give you all the information you need about this ratio, which I recall was computed as product of I equals 0 up to n large n minus 1 of the norms in the V case divided by the norms in the V0 case. All right? So I return now to this equation. So you see V is a polynomial, V prime is a polynomial. V prime of Q is just Q minus sum of qk over, sorry, 2k minus 1, and then the 2k, which was in the denominator, has gone in the derivative, and there's a g2k in front, k equals 2 to d. Okay? So basically, we have to understand what it means to take a certain power of q in this expression here. Okay, so the interpretation was in terms of paths. So q itself is easily understood as generating paths, n being the height at which you start, and you can go at height n plus 1 or n minus 1, so step plus or step minus. But when you go at height n minus 1, you pick up a weight which depends on where you started from. So there is this Rn here. So let me give you two examples. So Qpn, Pn minus 1 over Pn minus 1, Pn minus 1, it's trivial. You pick up the coefficient of Pn minus 1 in Qpn, right? Qpn is this, the coefficient is Rn. So this would be the degree 1 equation in here, okay? Now let's do a bit more complicated, Q cubed. Okay, so what is it? So you need now to look at paths of length 3, which start at point n and end up at point n minus 1, right? Height n minus 1. So you have basically 3 paths to look at. And, okay. So it's clear now, you have three contributions. So the first contribution will be an Rn plus 1 times an Rn, plus second contribution will be an Rn times an Rn, and the third contribution, n minus 1, n minus 2. Okay, so it's Rn times Rn minus 1. Okay? So in particular, in the case of tetravalent maps, what we get is this minus g times this. Okay? So for the tetravalent maps, we get n over n is Rn minus g times Rn, Rn plus 1 plus Rn plus Rn minus 1. Okay? So you have to feed, of course, initial data. So the clear initial data from this definition is that R0 should be 0. Okay? So you feed this initial data in there, and then you have a recursion relation. And at the end of the day, you're supposed to translate everything in terms of h and plug the h's back into this equation. Okay? So parallelly, of course, you have a quadratic term, the quadratic potential, case, V0, in which, of course, you only have the first term. So n over n equals Rn. So here there is no work to do. In the case of a Gaussian, you have orthogonal polynomials. And if you remember your list, favorite list of orthogonal polynomials, these are actually the Hermite polynomials with a different normalization. But this is Hermite. Has to do with Hermite. So the PNs basically are something like Hermite polynomials. So this gives you access to this ratio and then the generating function you like. Now, what I want to do right now is give you sort of a shortcut, which is a direct interpretation of the quantity R big N. So directly interpreted as actually itself the generating function for certain maps, but for some particular maps, as the GF generating function for tetravalent or higher valencies, okay, depending on whether you put more G's in there. So let's say maps, but okay, with 2 univalent vertices. So on top of whatever valencies you're allowing in your map, I'm also adding up 2 univalent vertices. So let me just draw a picture in the tetravalent case, okay? So you remember my very nice way of generating tetravalent maps, which is with circles like this. And now we'll have a univalent vertex somewhere and another univalent vertex elsewhere. So they are distinguished, okay? And the usual thing you do is that in the depiction as an embedded map in the plane, for instance, you will always write one of the univalent legs in the external face, okay, the face that contains the point at infinity. Whereas the other one can be very deeply hidden inside my map, okay? So my claim is that Rn will be interpreted as a geometric function for maps with 2 univalent vertices. And now there will be a weight n to the 2 minus 2h, where h is the number of holes, so the genus of the minimal embedding. And there will be weights g2k per 2k valent vertex. Okay. And now you remember there was this nasty question of the automorphism group factor, inverse factor, that you would have to put in there to have a correct counting. But here, things are much nicer because we have fixed basically all the ambiguities with these 2 marked univalent vertices, and therefore there is no extra weight. Okay? And oh, yeah, connected. Of course, these are connected. These are for connected. Okay? So what I'm going to prove to you is that this quantity Rn is actually what you expect it to be to describe such a situation. Okay, so what is this situation compared to what we did last time? So these 4 valent, maybe I should use another color. These 4 valent vertices, you remember, they were actually really these double-edged crosses, okay, in my construction with orientations. Okay, and those yellow lines being carrying indices of the matrices, etc. Okay, so the question is, what does this correspond to? So let's use orange. So what this is here, so it's trace of M, as you will see. So it corresponds just to having, again, a matrix element like this. But now I do a little loop here. That is, I identify the 2 indices of my matrix. Okay, this is what makes these end vertices, if you want. And this is exactly trace of M. Whereas these yellow vertices corresponded to trace of M to the 4th. Okay? So this is just the, okay. So now you see that in terms of matrices, I expect this Rn to be just given by trace of M, okay? The meaning of those double brackets, any function of M, is just that I do the integral with respect to this matrix measure. But now I normalize by the matrix measure itself. So if you want, this is my theorem. Okay, I'm going to prove this for you. Okay. So notice that the index here is large n, which is the size of a matrix. So from the point of view of these equations, you would be really at the border of a domain of definition, which is when small n is equal to big N. Okay? Keep that in mind. All right, so why is this true? Well, how would you go about computing? You see, the computation of z of nv and the computation of this numerator here, when for f of m I put trace m squared, is almost the same. So let's just follow again all the steps we went through to compute z of nv, but now with a spectator, if you want. Okay, so first step was to go to eigenvalues, right? So we were writing, so now I'm concentrating on the numerator here, which would be integral dm, trace m squared, e to the minus Sn trace v of m. Okay, and I'm trying to compute it in pretty much the same way as we did before. So there was the first passage to eigenvalues. So it's still perfectly smooth. Okay, you have a Vandermonde of your eigenvalue squared. Now trace of m squared, I can write it down directly as sum of lambda I squared, 1 to n. And then there's the product of E minus n, V of lambda I equals 1 to n. The trick we used with the orthogonal polynomials, we still use. Okay? So I rewrite this as integral d lambda 1, d lambda n of determinant of pj minus 1 of lambda I determinant pj minus 1 of, okay, I shouldn't probably be using the same letters. And here, KL. Okay, so my product of two determinants, basically, in which I have stuck my, my monic orthogonal polynomials instead of just the powers. And then, well, how about putting this thing, product of d lambda I e to the minus n v of lambda I put it in the measure. And then we have somewhere here this spectator, which is sum of lambda I squared. Okay, so we expand again as a double sum over permutations. Okay, same trick. So I reassemble. Okay, so let me do it quietly. Okay, so these are my measures of integration. Sum of lambda I squared. And now signature of sigma tau. So the sum was over these two permutations in Sn. Okay, signature of sigma tau. And then P sigma of I minus 1 of lambda I, P tau of I minus 1 of lambda I. Okay, so here just a little trick, which is that, okay, so we are supposed now to expand this sum of lambda I squared, right, as basically sum of lambda I squared from 1 to n plus sum I, say, less than j, twice of lambda I lambda j. Okay? And you see this expression, now this integral here can be redistributed on every term individually. Okay, so I have two types of term, I claim. I have terms of the type lambda 1 squared, which will contribute for something, and I have n of them. And I have terms of the type lambda 1, lambda 2. And I have n minus 1 over 2 times 2, so it's n minus 1 of them. Okay, and by this bracket here, well, I don't know. I need yet another. Okay, I use this notation, but what this means is just the integral. That I get from just actually doing these things, okay? So in the case of lambda 1 squared, you see that basically I'm saying that I'm integrating lambda 1 squared times this product of orthogonal polynomials with respect to those measures. Now, you see that in the product, I will have lambda 1 squared times p, whatever value of sigma gives me the value of 1. So it's sigma of 1 minus 1 of lambda 1, p tau of 1 minus 1 of lambda 1. Okay, and I can do this integral completely independently. Okay, and then this comes multiplied by the rest of the integrals, which are product for j different from 1, therefore j equals 2 to n, all the rest of the polynomials which appear here. And then I have something very simple, because I have just p sigma of j minus 1, p sigma of j minus 1. Okay? Now, these brackets, well, Okay, I can go slowly, so let's take this as a definition for my brackets. And you see that whatever result I get for lambda 1 is the same for lambda 2, for lambda 3, for lambda 4, because of symmetry. Okay? Now, interesting thing again, these are orthogonal polynomials. So I deduce that for everybody except j equals 1, I must have the same value of sigma. Well, therefore, j equals 1 also has the same value of sigma, right? So again, just from this, I get that, sorry, that was tau. I get that sigma must be equal to tau again, all right? So this is just a bunch of products of norms, okay, except the norm that will appear at sigma of 1 equals tau of 1, okay, which I can give a name to it, m, okay? And of course, here summing over sigma and tau will sum over this value of m, okay? So eventually what I get is that just q squared p m minus 1 p m minus 1, which would be just this integral, times product of hj from j equals 0 to n minus 1 j different from m. Okay, so I probably need to write j from 1 to n to be correct. This is going to be the same m here that is missing. Okay, and this is what this quantity lambda 1 squared is computing for me. Okay, so now q squared pm minus 1 is just r m minus 1. Okay, because of the definition of a q operator acting on the orthogonal polynomial basis. So that's one term. And then we also have to compute the lambda 1, lambda 2 term. Okay, and the lambda 1, lambda 2 term is a little bit more delicate because it will involve both the integral over lambda 1 and the integral over lambda 2, and then the rest. Okay? So we repeat this exercise, but now we have two integrals. There's a d lambda 1, lambda 1, times p sigma of 1 minus 1 of lambda 1, p tau of 1 minus 1 of lambda 1 e to the minus nv of lambda 1. That's the lambda 1 integral. Then there is the lambda 2 integral that comes right next to it, which is of the same kind, basically, d lambda 2, p sigma of 2 minus 1 of lambda 2, p tau of 2 minus 1 of lambda 2 e to the minus nv of lambda 2. So this is the lambda 1, lambda 2. And then in factor of that, I will have all the rest. So that will be the product over j from 1 to n. Now j different from, well, this value and that value, and that value. So we're going to have to give them names. So let's call them Lm for the time being. And there will be aj's again. So we are basically missing two values of the norm, which are going to correspond actually to whatever values I read in this part. Okay? Now, it's a little bit more complicated than before. You remember that lambda 1 itself is just the action of q. Okay? Now, q changes the index. It cannot preserve the index. So these two guys are not equal. So this is just a transposition. Okay. It's the same quantity. and times product j different from L and M of hj minus 1, j minus 1. Okay, and what do we know? We know that QPL is PL plus 1 plus RL PL minus 1. So PM doesn't have many choices. It can be either L plus 1 or L minus 1, right? And you will check, of course, that the other quantity, one quantity will give you 1, and the other quantity will be the R. So among those two quantities, again, you're going to get 1 times RL, basically. Okay? So if I put everything together, what I get in the end, and if I divide out by, so this was the numerator here, I divide out now by the full integral, and the full integral, I recall, was this product of norms. Well, from 1 to n of hj minus 1. So if I divide out by the product of norms, you see there's a whole bunch of things which are going to go out. Well, I forgot, of course, that I was summing over permutations here. So here I have fixed one value of a permutation, so I still have a factorial n minus 1 in front from the summation over the permutations. And here I have fixed everything but two values, so I have an n minus 2 factorial in front. Okay? And in the denominator, I recall that I was summing over permutation, so I had a factorial n in front. Now you see everything is well behaved. This n combines with the n minus 1 to give an n factorial. The n minus 1 combines with the n minus 2 to get an n factorial again. So all the factorials disappear. Everything is nice. And well, trust me, in the end, you get just a sum of r's minus a sum of r's. And it's well behaved enough that in the end, you just get one r. Okay? So the result of this calculation is just giving you Rn, okay, as being this average with trace of m squared in the numerator, which we have interpreted as enumerating, so tetravalent maps with two very special vertices, okay, which are both univalent, okay? So to summarize also, what we expect, of course, is that when n goes to infinity, only the planar maps will dominate. And this Rn is going to tend to a finite limit R. Okay? So now, what does this Rn satisfy for an equation? I recall that we had small n over big N, in the case of quadrangulation, was Rn minus G, Rn plus 1, plus Rn minus 1. Okay, so if I take, in particular, small n equal big N, I get 1 is Rn minus G Rn, Rn plus 1 plus Rn minus 1. Okay, now if I know that this guy converges, of course, Rn is going to converge with a unique solution of 1 equals R minus 3G R squared. Okay. Unique, well, it's a quadratic equation, so there are two solutions. So how do I fix my solution? I will fix my solution by saying that when G goes to 0, well, R should tend to 1, okay? So R is basically 1 plus O of G. Okay, and what is R? R is 1 minus square root of 1 minus 12G over 6G. That's what you get from solving this quadratic equation. And here, everybody will recognize the generating function of Catalan numbers, except that the normalization is slightly different than usual. This is just the sum, n larger or equal to 0, of 3 to the n, Catalan number n, times g to the n. So here, I recognize, actually, the cardinality of this set that was called, I believe, Tn, right? Okay, so the objects that seem to be forming the planar limit of these maps I was looking at with two univalent vertices are actually enumerated by those labeled trees. Okay? So more generally, I think it's worth to mention it because it's very easy to derive. More generally, if my potential, I mean my function v here, was the more general polynomial v of x is x squared over 2 minus some g2k x2k over 2k from 2 to d. Okay, if I had this as a more general case, then of course v prime of q would be q minus some g2k q2k minus 1. Okay? And I would have now to write down an equation, n over n is equal to Rn minus G4 times whatever I found for the case of 4, etc., right? Where the G2k term, I recall, was just a sum over the paths of length 2k minus 1, which were started at height n, and so after, doing whatever they want to do, ending at height n minus 1, and with all those weights, with this collection product of r picked along the way. Okay? But what is clear here is that you see the size of your path is k, is the order of k, right? K is bounded because we are looking only at finite degree polynomials here, right? Now, as n, large n, is going to become very large, if we look at the neighborhood of large n, which is small n equals big N, this calculation essentially didn't rely at all on the fact I was looking at the quadrangulation rather than the more general case, so I can repeat it. So this Rn, interpreted exactly in the same way, but now with more general maps, is actually going to obey a more complicated, a higher degree algebraic equation, which is just 1 equals R minus some k larger or equal to 2 of G2k. And here I will have just the number of paths of length 2k minus 1, which starts at a given height and end up at a height 1 less. Okay, so if you forget about n, basically, because n is large n, and large n is going to infinity. So we have now those paths of length 2k minus 1, which starts wherever here and end up 1 less there. And you know that there will be one more step down than steps up. So there are k steps down and k minus 1 steps up. So the number of those paths is basically this combinatorial number. And then there will be an r to the k, because there are k descents, and you are picking an r at each time you were making a descent. If you want, it's as if I was approximating my q operator by qpn is pn plus 1 plus r pn minus 1. Okay, and this n being large, I replaced the Rn by r its limit. Okay? So this is the equation. And the claim now is that, well, exactly the same thing as before. The generating function for planar maps with two univalent legs, well, I call them legs, vertices. Okay. So connected, even valent. Okay, with weights G2k per 2k valent vertex. Okay, is this R, which is the unique solution to this algebraic equation, which has a nice power series expansion in the G2Ks. Okay, so basically R equals 1 plus order of any Gs. Okay, all right. So this was just to motivate somehow why it was so important to find the trees hidden behind the maps. It's because these algebraic equations are very simple, are too simple, actually. We seem to have broken into an open door here by this heavy machinery. Okay, one can do more, of course, because we can go beyond planar maps and enumerate also higher genus maps, okay, because these equations were exact, so they allowed to go beyond. But in as much as understanding the trees behind the maps, this didn't really help. This just gave the results somehow, right? So let me now show you with slides, because it's more pictorial, where the trees behind the maps are. And you will see these are not quite the trees that Gregory showed in his lectures, but it's more like the dual version. Okay? So should we move this? Okay. I'll let you do it. Should I disconnect and reconnect, maybe? Okay. Projectar computador. Ouais. So maybe I just disconnect and reconnect. It worked before, so. Okay. Okay. I have an idea. There we go. Okay, good. So you recognize on the left my picture, right? It's this tetravalent map with two univalent vertices, which I call in and out. Okay. Thank you. Ooh, nice. Okay. All right. So in and out. So I choose to represent in the outer face, like I said. Okay. So now there's this bijection. So it's not CVS. I think it's really S. It's Schaeffer. Okay. So actually, he came up with these two sets of bijections, which are sort of dual of one another. So here I'm talking about the first set that he found. Okay. And so there is a bijection between tetravalent maps, so planar, connected, blah, blah, with two legs labeled in and out, and what are called rooted tetravalent blossom trees. So they are plain trees like the ones Le Gall described in his lectures. But now we have leaves of two kinds, which are depicted white and black. So blossom trees would be, I think these are called the buds and these the leaves in their terminology, okay? And the characterization of these rooted tetravalent blossom trees is that they have exactly one black leaf hanging at each vertex. Okay, so plain trees. Very important thing. I represent my trees as hanging from the ceiling and not growing from the ground. Okay, this is the major difference. But I have a good reason for that, but I can explain to you later. It has to do with ancient German history. Okay, so anyway, so I represent the root on the ceiling, basically, and my tree is hanging from the ceiling, and it has one black leaf at each vertex, okay, and it's tetravalent, okay, and so it ends up with leaves, all right, so in this case, I have 1, 2, 3, 4, 5 white leaves, and of course, one less 4 black leaves, okay, and this will be a characteristic property also, that there is always one less black leaf than white leaves, okay, but this is the characterization here. Okay, now how does this bijection go? So let's hope this thing does it right. It's too big. I knew something would go wrong. So it has to be slightly smaller, otherwise it doesn't work. Okay, still too big. I'm sorry. Almost. Okay, there we go. So the idea is that we start from this in vertex up there, and we start walking. You imagine a walker which does something like a contour walk, if you want, but he's actually walking along the border. Okay, he's not allowed to cross the border. So he walks along the border of the external face, the face that contains the point at infinity on my sphere. Okay? Right. Now, along the way, what he does, he's not totally harmless. He has a pair of scissors. And what he does is he cuts the barbed wire along his way to pierce a hole in the border. Okay, so it's kind of a nasty character. So he's piercing holes in borders, and he goes like this around his border. Okay, and the thing is that he will be allowed to cut the edge, even only if that edge cutting doesn't disconnect the picture. We started from a connected map, and whatever picture we are going to come up with in the end still has to be connected. So the only rule is that you will always cut, except if by cutting you disconnect the rest. Okay, so now he did his first round. So what he does is the following. So it's a bit quick. Each cut edge here is going to be replaced by a black followed by a white leaf. You see, now I will have a leaf hanging from this vertex and another leaf hanging from that vertex. And somehow I have to remember in which order I did this cutting. So wherever you come from will be the black leaf, and wherever you go to will be the white leaf. Okay, so let's see if you can. So just concentrate on this guy here. Okay, and hop. Okay, so here is the black leaf you came from, and here is the white leaf you go to. And I did the same to all the others. Okay, so I have now a new map, now with leaves. Okay, so these leaves you can think in terms of maps as being univalent vertices, right? They are new univalent vertices from a point of view of the map. Okay, so we are at round 2 now. At round 1, we cut the external face. So we still have a map. So we still have an external face, which is way bigger now, if you want, because many of the faces of the previous map have been merged with the outer face, with the face at infinity. But I can still do my same algorithm. So, okay, boom, I go around. So you see now my contour is a bit more complicated. I have to go in all the holes I have pierced, basically. And again, I can cut whenever I don't disconnect the picture. So let me show you a place here. Okay, so you've been traveling this way, that way. Here you've cut. Okay, now you arrive here, and here you cannot cut. Because if you cut here, you would detach this piece. Okay, and we don't want to detach anything because we want a connected object in the end. Okay, so well, then you go on. All right, so let's go quickly now. And in the end, this is what you get. You stop, of course, when there is nothing else to cut. Okay, you could, of course, continue round 3, round 4, but then there is nothing else to cut. So you stop when there is nothing else to cut. And now, what you do, you remember I had an in univalent vertex and an out univalent vertex. So I promote the in vertex to a white leaf, and I promote the out vertex to the root. Okay, and now I hang the whole thing from this. So I attach it to the ceiling up there, and whatever is under it will be my blossom tree. Okay, so this is the bijection in one direction. Okay, so what have I got in the end? I've got, yeah, there is some text under here, actually. There we go. So, so what we end up is a blossom tree. And I claim here are the properties that you get just from this procedure, which is property P1 and P2. There is one black vertex attached to each vertex. So look here, for instance, there is one black and only one. To this one, there's only one black. This one, only one black, etc. And property P2, the total number of white leaves minus the total number of black leaves is, well, something I can call n white minus n black, and it's equal to 1. So I call this sort of a charge. So I attach a charge +1 to the white leaves and a charge -1 to the black leaves. Okay? And then I say that the total charge, which is the sum of all the charges of all the leaves, is equal to 1. Okay? The algebraic sum, because these guys are in negative charge. Okay. So how do I prove these properties? So P2 is absolutely clear. Why do you have one more white leaf than black? Well, remember, I got my white and black from cutting. Okay, so they always came by pairs, black and white. Okay, and then at the end of my process, I promote one of the univalent vertices to a white leaf. So it's clear that there is one more white leaf than black. That's trivial. Now, the other property is more interesting. It's a sort of conservation property, actually. And you will see that this is actually responsible for the integrability of the whole thing. So I think this is important. So it's worth spending a little more time on it. So P1 can be rephrased as the following. Okay, that each descendant subtree in this big tree hanging from the ceiling has total charge +1. Okay, so what do I call a descendant subtree? I pick an edge anywhere in my tree. Okay, there are two pieces. There's the piece of the tree which is above my head, in a sense, which contains the root, and the piece of the tree which is under me. Okay, so you would call it descendant, of course, if you have wanted to interpret this tree as a genealogy. Okay, so that's why I call it descendant subtree. Okay, now if I concentrate on one of those edges with the root of my head, okay, then I see the following. I have to remember that this edge, which remains in the end, actually has seen many of those rounds turning around it while I was cutting. You see? So there is a part from the black and white leaves which are going to be connected to each other in the bottom, and the black and white leaves connected to each other in the top. There are the pairs, black and white, which comes from edges in the map that were connecting vertices from the top to vertices from the bottom, and vice versa. Okay? And the claim is that because I have made a finite number of rounds around my center edge here, there can be only M and P such black and white and white and black on the bottom, such that M equals P or P plus 1, depending on whether you stopped on the bottom piece or you stopped on the top piece. Okay? So this is pretty clear. But of course, I have something which says me is that I'm dealing with even valent vertices here, actually 4 valent vertices. So a map with 4 valent vertices, if I cut this edge and cut that edge, I have to count how many external edges I am left with, and this number has to be even. So it means that M plus P has to be even. So M is P or P plus 1, it can only be equal to P. Okay? So therefore, if M is equal to P, I can now count the charge, right? M plus P, the charge is minus M, and the charge is plus M. So the total charge of the top piece is 0. And in the bottom, I also have M and P, but I have this extra edge, which was the in leg promoted to a white leaf, okay? And I claim it has to be on the bottom because, again, of this parity property, okay? So m equals p, and I have this extra guy hanging below. Therefore, the total charge of the bottom is actually 1. So total charge 0 above, total charge 1 under. So it is true that by my cutting procedure, I end up always with a tree such that each descendant subtree has total charge plus 1. Okay? So after this lemma, it's piece of cake to show that you have exactly one black leaf per vertex. You start from the outer vertices, right? The vertices which are connected to only leaves, okay? There, it's clear that to have a total charge plus 1, you need 2 white edges and 1 black, okay? Then you cut this and you replace it by an object of equivalent charge. So you replace it by a white leaf, and you continue, okay? So if you do this grinding algorithm, which goes back inside my tree, you will see that at each vertex, you need exactly 1 black leaf, and that's exactly this property of having 1 black leaf at each vertex. Okay, so I think the properties should be clear. Okay, now there's the question of why this is a bijection. Well, the thing is that these black and white leaves are enough information to go back to a map. Okay, so this is not obvious a priori. So you have to find a way of closing back the whole thing. So I'm still taking the same picture, of course, but now I assume I don't know of which map I came from, and I'm trying to reconstruct the map. Okay? So here the question is, there are 2 questions. Why is this leaf here the loser? Right? There is some, it's the musical chair games, right? You have mates, but one guy doesn't. Poor guy, but that's life. He's not going to have anybody to match to. Okay? Now, I'm claiming that just by staring at this picture, I already know who the loser is. Okay? It's this guy and nobody else. Now, I also know who's going to be connected to whom. For instance, this, what I call X here, is going to be connected to Y here. And I know that, okay, just by staring at this picture. Okay, I know, but you don't, so let me show you how. So there is the notion, again, of a sort of contour walk. So it's not the same notion as described in the lectures by Le Gall and Mirmont, but it's very similar. So now, here is the thing. I'm going to walk around my tree. So again, in the same order. So I start from the root here, and I do exactly the same contour as they were doing when they described the function C and the function V. But now what I record is just whenever I have a white leaf, I will go up, and whenever I see a black leaf, I will go down. Okay, so I create a path, which is therefore not necessarily a dict path, okay, but which tells you basically along the way what I encounter. So here I encountered white leaf, here black leaf, white, black, black, etc. So it's the collection of colors of leaves you encounter on your way. Okay? And now, if you want to know who is connected to whom, what you're going to do is actually connect horizontally by lines, okay, the descents and the up steps, right? The descending steps and the up steps that are across each other will be connected. Okay? So this takes care of everything that's in these valleys and above those valleys. And now I have to tell you how to connect the boundary here to the boundary there. And it's just a recipe, which is that you have to sort of shift things by 1 in height, and then you again connect to your partner on the other side. Okay? So this connection here is well defined and uniquely defined, and it leaves this poor guy here, musical chair loser, because he has nobody to connect to. Okay? So this is one way. There are many other ways. You could also say something like you're going to connect each black leaf to the white leaf immediately following it in the contour order. Okay? So for instance, this black would be connected to the white immediately after it. This black doesn't have a white immediately after it, so it will have to wait until this guy is connected to this next, and this guy connected to its next, and then he will have a chance to be connected to its next. You see, there is an onion structure, basically, right? You've peeled the whole thing like an onion, and now you're reconstructing it also like an onion, okay? All right. So I don't go into more detail. I prefer to go immediately to the comparison with this result of the matrix model, okay? So the enumeration now. So we have R, the generating function, now for these maps, of course, but because there's a bijection, it's also for rooted blossom trees with a weight G per vertex. Huh? G was a weight per vertex. You see, we're doing sort of a dual thing as was done by Gregory. Huh? Okay, so there's this equation, which we know already, and now we can interpret it in terms of those trees counting. So I have this picture for whatever blossom tree is hanging from the ceiling. Okay, so this is R, the generating function. So I put them all in the same box, if you want. So what can happen? Well, either it stops immediately and there's no vertex. So it has to be a white leaf. It's the loser. Okay, or there is a vertex. So there is a weight G for this vertex. And there are basically three possibilities, which are the three situations in which the black leaf is either the leftmost, the center, or the rightmost. Okay? So you get this equation here immediately from enumerating those blossom trees. And here we see that it's just a matter of enumerating binary trees. And there's a three at each vertex, right? Because these are the three positions at which you can attach the black leaf at each vertex. So 3 to the n, Catalan n. Now, this was, strictly speaking, holding only for tetravalent maps, but you can repeat exactly the same story for arbitrary even valencies. Okay? So now, a blossom tree, what's the correct definition in order to have a nice bijection will be same thing, rooted tree with white and black leaves with valencies which are basically the same valencies as the maps you're considering, and such that each descendant subtree has total charge plus 1. Same property, irrespectively of the valencies now, which can be whatever they want, the degrees. Okay, the theorem being now that there's a bijection between the two univalent or two-leg planar maps with valencies or degrees 4, 6, 8, whatever, any even number, okay? And rooted blossom trees with same valencies, okay? The definition being, again, that you have trees which are rooted, which are plain trees, and then they have these white and black leaves, and there's, for each descendant subtree, there's one more white than black. Okay? So the proof, well, is basically the same. That is, it's the same cutting algorithm. You go around faces and you cut whenever you don't disconnect. The characterization now is slightly more subtle. You find out very easily because of this condition that there is one more white than black, basically, but at each vertex now, each vertex of valence 2k must have exactly k minus 1 black leaves. So if k equals 2, valence 4, there was one black leaf, right? But okay, k equals k, you have this. Now, how does the enumeration go? And that's where really things are arranged very nicely. So again, I write this blob for the generating function of my blossom trees now with vertices of even valencies and weight g2k per vertex of valence 2k. So two things can happen. Either I have no vertex, therefore, again, it's just 1, and I have just the loser leaf, if you want. Or I have at least one vertex. This vertex will have a certain valence, let's say 2k. Of course, I have to sum over all possibilities, so I have to sum over k here. And if the vertex is 2k valent, I now have to enumerate all the possible inequivalent geometries here, that is, ways of putting k minus 1 black leaves among 2k minus 1 slots, right? So this is this combinatorial number, 2k minus 1, k minus 1. And this r to the k is for the remaining k blobs here, and each blob is itself a descendant blossom tree, okay? So now you look at this equation, and you look at this equation, and these are the same equation. Okay? So this is really the tree interpretation of this rather complicated result that was gotten first. Well, I think Chut actually got it first. Maybe not exactly in this form, but that you can also recover from matrix models. Okay. So far so good. So now I want to show you how these tree bijections allow actually to go beyond the matrix model. So the matrix model, I explained, allows to go in one particular direction, which is enumerating of higher genus maps, okay, which we haven't covered here at all, but I just mentioned that. Now, the other direction is, of course, to try to keep track of geodesic distances, which is exactly what we are going to do here in the language of those blossom trees, okay? So basically, what's the geodesic distance between the two legs in my tetravalent maps with two legs? Is just the minimum number of edges crossed in a path. So that goes from one leg to the other. So here, for instance, in this example, the geodesic distance between the in and out is 2, because no matter what path you're going to take to go from here to there, you're going to have to cross 2 edges. Okay, so 2 is the minimum number of edges. Of course, if you go through vertices, it doesn't count. So you have to have some sort of generic paths that don't go through vertices. Okay. All right, so now here is the interpretation I want you to have in mind when we do a further enumeration. I think this is really the interesting part. Via the bijection, D is how deep the root was inside my onion, right? I had to go several rounds around the onion and cutting several edges to liberate this guy so that he could breathe some air from the outside. Okay? He was prisoner inside. So how much is he prisoner? It's the number of edges I had to cut to liberate him. Or how many turns around the whole maps I had to make to get to the point where it would be connected to the outside. So this is this D, right? I call it the depth of the root. And now, how do I interpret it? Well, if I consider only the edges that were separating this root from the outer world, okay, there were a number of black leaves here and white leaves there, which by pair would be connected to recreate the edges of the map that were separating it, okay? So I only represent them. And I ask you to think of the D as just the number of black guys to the left of this root that will not be reconnected without going around the root. Okay, so these are, if you want, sort of excess black leaves on the left, which are not going to be reconnected to anything before passing the root, right? They are in excess, if you want. Okay, excess black leaves on the left is the number of excess black leaves on the left is the distance that separates the root from the other vertex. Okay? So let's now enumerate Rn. Okay, I'm sorry for the notation Rn, but I do it on purpose, actually, not to confuse you, but to really show you that there is a hidden connection between the two problems. But the definition is completely different from there. Okay, so forget about the definition there. Rn is the generating function of rooted maps, okay, with two legs at a geodesic distance less or equal to n between the two legs, okay? So less or equal. It's important to have less or equal because once I have made this definition, here is the enumeration. It's sort of a completely immediate refinement of the previous enumeration of trees. So now I told you to think of this index n as being the number of excess black leaves on the left here that are going to be reconnected only by passing above the root. Okay? So now I want to enumerate this Rn. So again, either there is no vertex and then it stops with 1, nothing to say, or there is a vertex and then there are a bunch of things hanging from that vertex. And we know already that there will be 1 black leaf and two trees, and just these 3 situations. But now, I want to keep track of the maximum number of excess leaves that will give rise to edges passing above the root. Okay? And I claim, okay, let's concentrate just on this first configuration here. I think it will be enough, and then you can reconstruct the others. So the claim is that this first will correspond to G, which is the weight for the vertex, times Rn minus 1, which will be the weight for the generating function here, times Rn, which will be the generating function here. Okay, so here we have a black leaf already in excess. We know already that this guy will have no choice but to connect to the other side, right? So that will create already one edge passing above the root, okay? Now, how many at most can occur from this piece? Well, n minus 1, because I already have 1, okay? So this piece will be Rn minus 1. Now, here is more delicate. I know already that this Rn minus 1 piece has an excess white leaf. It's the loser, right? The local loser here. So that local loser is going to be, is very happy actually to be a loser here because he's going to be satisfied. He will be connected to one of the excess black leaves coming from this guy, okay? Therefore, again, in total, I can allow only at most n minus 1 black leaves passing. So I can allow n here because one of them will be connected to one here, okay? So you get this product Rn minus 1 Rn. So this is really the interesting equation I want to draw your attention to, which is that with that definition of generating function with geodesic distance smaller or equal to n between the two legs, I have actually a closed formula, which is a recursion relation in the geodesic distance m. Okay? Well, I will have these slides printed, and you can think about it looking at the pictures. Okay, so here is my recursion relation for tetravalent maps. What are the boundary conditions? Well, the boundary conditions are basically, you remember, n is the maximum number of edges passing above your head. Of course, there is no such thing as less than minus 1, and r minus 1 has to be 0 if you want, because when you stick n equals 0 in this equation, it has to make sense with no term here. Okay, so r minus 1 is 0 is my first boundary condition. Second boundary condition is kind of, these are not really Cauchy boundary condition because there's one initial condition and one final condition, basically, which is that if I remove this constraint on the distance, then I get the previous enumeration, right? The one without a constraint, which is r. R, the solution of the equation r is 1 plus 3gr squared, okay? So this Rn actually tends to a limit, which is r. So equation, boundary conditions, can one solve? Okay, so there's one way to solve which is kind of stupid. It uses the fact that the R's all have a power series expansion in G. So you stick into your equation the various beginnings of power expansions and you iterate. And that gives you, little by little, all the coefficients. So with a computer, of course, that would be the easiest way. Okay, and the limit is stabilized in the sense that Rn minus r, see, Rn tends to r, but actually Rn is already equal to r up to order g to the n. Okay, so it's a pretty nice situation. So on a computer, that goes really quickly, but you can do better, actually. So this recursion, and that's why I went through all this trouble in the first lecture, this recursion is actually integrable, both integrable and exactly solvable. So let me show you, first of all, why it is integrable. So here is the theorem. There is an integral of motion. So you remember, I showed you already an example of a three-term recursion relation, which involved Rn minus 1, Rn, and Rn plus 1, okay? Of which we extracted one integral of motion linking Rn and Rn plus 1, okay? Same thing here. I claim that this function of Rn and Rn plus 1, which is of degree 3 now, one more than the equation we started from, but involving only two terms, n and n plus 1, okay, is conserved modulo the equation. Okay, so if you want to prove this, you just check the following identity. Huh? You do the difference at two consecutive values, okay, and then you find out that there's this term which comes in factor, and in factor of what? Of precisely the equation. Okay, so modulo the equation, this quantity, okay, will be the same here and here, right? The difference is 0. Okay, So you could wonder, okay, this is like black magic, so where does it come from? Okay? So it comes from a very simple property of the blossom trees, which was this fact that there was always a loser. Okay? So here is a new definition. I define the depth of a leaf to be an integer j if it was cut at the round d minus j plus 1. You remember I had a first round where I cut the guys connected to the face at infinity, and then a second round, etc. So if I cut it at the round d minus j plus 1, I will call j the depth. So if you want the depth, would be 0 for the loser, because it never was cut at any round, if you want. It's the last guy standing, basically. So the loser has depth 0. The guy is cut just before the last time will have depth 1, etc. So your depth is basically how deep you are, right? So depth, okay, fine. So we have the following property, which is that in any blossom tree, the number of white leaves of depth less or equal to n minus the number of black leaves of depth less or equal to n is equal to 1. Okay, so this is just this property of the existence of one loser and only one, right? There's always one more white than black leaves, okay? Now you use this property and you enumerate blossom trees with marked leaves. So you're going to either mark a white leaf of depth less or equal to 1 or a black leaf of depth less or equal to n, okay? So the enumeration is quite simple again, because if your white leaf is of depth less or equal to n, what you can do is swap that leaf with a root and find out that what you're actually considering, the generating function of those objects, is just Rn. Because now you have a leaf and you have n guys passing above it at most, which is this condition of being of depth less or equal to n. Okay, so this is Rn, is basically the enumeration of the first guys with a marked white leaf at depth less or equal to n. And the enumeration of the second set of guys here will be a black leaf at depth less or equal to n. And then you just think about it a little bit, and you will find that, again, it's a product of three generating functions with Rn minus 1, Rn, and Rn plus 1. So the conclusion is that the following quantity, Rn minus g Rn plus 1 Rn Rn minus 1 is a constant. And actually, this constant you can calculate. It's R0. OK. So there is a conserved quantity here. Now, what does it have to do with my conserved quantity of before? Well, you just compute that whatever this polynomial was is actually the equation times something minus this quantity we just got here. So it's equivalent, if you want. The conserved quantity is due to this conservation. Okay? So now, using that conservation, you can do a lot of things. You can plug in the boundary conditions in this equation, right? So for instance, you find that phi of R minus 1 R0, R minus 1 was 0. So it's just minus R0 from the definition. And now at infinity, n going to infinity here, you will get phi of R and R. So you get immediately R0 is R minus GR cubed. What is R0? R0 is a generating function for maps with two univalent vertices, which are both at distance 0. Okay? It means they are in the same outer face. Now, if they are there, both of them in the outer face, you could, of course, connect them and make a closed tetravalent map out of them, right? And that's basically the rooted tetravalent maps, right, that I think Gregory showed us in the dual version. Okay, and you remember there was an edge which was marked and oriented. And here, of course, you can orient from the in to the out, let's say. So this is the same generating function. And it's expressed in a very simple way in terms of its R, which was just a generating function of Catalan numbers. And if you remember, there was this formula, something like 2 over n plus 2 times 3 to the n Catalan n for enumeration of those objects. So this 2 over n plus 2 is basically what you get from this difference here. That's another way of saying it. Okay. But this was also derived by Tut in his old papers. Okay, and then in particular, you get the asymptotics of this number of tetravalent planar maps with n vertices, which goes like 12 to the n because of this 12 here. And there's this 5/2 exponent, configuration exponent. Okay, I don't go through this. I don't think it's interesting. Okay, now the other interesting question is, of course, I showed you that the equation, the discrete equation, was integrable. And you remember the last time I showed you one, it was also exactly solvable. So question, is it exactly solvable? Answer, yes, it is. It means that there will be some sort of, not some sort, some associated linear recursion relation, okay, which will sort of govern the solution here, just like it did in the example I gave you on the first lecture. So here is really the heuristic way of getting it, but I think it's interesting to see the logics. We know that Rn tends to R when n goes to infinity. So we are going to expand it around its limit. Okay, so we'll say that Rn is R times 1 minus something small. So of course, if we plug this into this equation, what you can do naturally is linearize, right? Linearize the equation around the limit. Okay, so if you do that, you find this at order 1. Okay, at order 0, you just get the limit. Okay, fine. At order 1 in row, you get this linear recursion relation, which is just the linearization of this nonlinear recursion relation. Okay, so of course, the solutions here, this is linear, so we just look for solution in the form lambda x to the n, and x has to be solution of a characteristic equation associated to the linear recursion relation, and you get an x, which is a solution of this. Okay, so as rho has to be small, you certainly want the x with modulus less than 1, and you see it's a function of x plus 1 over x. So for generic G, there will be a unique solution with x smaller than 1. Okay, so you take this solution, and now you want to do things correctly. So the real rho n, not the linearized one, will have itself an expansion in powers of x to the j for j larger or equal to 1. Okay, so you expect this row to be expandable like this. So what you do, you write down, you plug this into the equation. This gives you recursion relations between the coefficients. It's lengthy, but at the end, you find something extremely simple and nice. You find that the solution Rn is actually given by this cross ratio formula. Okay, so x, I recall, was the root of a characteristic equation of a linearized equation around the limit. Okay, but this is exact now. This is for all n. Lambda will be an integration constant determined by the initial data. Actually, we already took into account the fact that at n large, Rn tends to R, right? Because this x is smaller than 1 in absolute value. So whatever lambda, it will tend to R. So we just have to say that at n equals minus 1, we get 0. And you see, it comes from this term. It will tell you that lambda is equal to 1. Okay? So it fixes this initial condition. And here is the final result. Rn is just R, the limit, which satisfies the algebraic equation there, times this cross ratio involving x. So this is the generating function, I recall, for two-leg planar tetravalent maps with geodesic distance at most n between the two legs. So something completely explicit like this. And this explicitness, if you want, is directly a consequence of the integrability here. And the existence of this linear recursion relation, which was associated, and of which x was basically the solution. X to the n was the solution. Okay? So, so this gives you a sort of different point of view on the same object, maybe a bit less probabilistic, but you can actually compute explicitly those generating functions. Okay, now it gives access to all sorts of things. Okay, so for instance, out of a generating function of g, of course, you can extract by just extracting the power of g to the n, the coefficient of the power g to the n in the expression of a generating function. You can extract properties with fixed number of vertices, right? the coefficient of g to the n corresponds to n vertices. Okay? So how do you do that? Just by a Cauchy type integral. Okay? So for instance, we have access to this very interesting quantity here, which is the ratio of the gn coefficient in Rn and the gn coefficient in R0. Okay. So how do I want to interpret this? So Rn are the two univalent vertex generating function, such that the distance is at most n between the two univalent vertices. So you can think of one univalent vertex as being the center of the ball, and the other one probing whatever's inside a ball of radius n. Okay? So you're basically measuring the number of points in a ball of radius n. So here you normalize just by the case where the 2 points are equal, therefore you're just sitting at the center. Okay? So now you can compute that completely explicitly. So you get actually a ratio of polynomials. Okay? But what you can prove, for instance, is that at large n, it tends to 3 over 56 times n to the 4. So this is the same n to the 4 that enters all these renormalizations of a contour of labels V in all the theorems you've seen this morning and last week. And here I really want to interpret it as a fractal dimension that is really the volume, if you want, of a ball of radius n around a vertex inside my map. So it means that your map viewed from a point is not at all a surface, right? It would go like n squared. And instead, it goes like n4. So I let you imagine what it looks like, really. It's kind of nasty. OK. So, all right. OK, so how to prove it? Well, you use my explicit solution here. You do a bunch of Cauchy integrals. I don't think it's very interesting to lead you through all this. But at the end of the day, you find a ratio of polynomials of n, so something completely explicit. OK. Maybe more interesting here is the scaling limit. So already in the expression for R itself, the limit, we've seen the emergence of this critical point. Which is basically giving rise to this branch root singularity. So this is something regular of G plus a constant times GT minus G to the 1/2. So a branch square root branch singularity, where GC is equal to 1/12. Okay, so for physicists, GC is called a critical point. If you want, it's the finite radius of convergence of your series. And by approaching, see, if you're looking at generating functions where G is close to this value GC, you're going to sort of blow out your series around maps which are very large. Okay, so a way of probing very large maps is to actually approach the critical point. Okay, so let's see what happens when we approach the critical point in our generating series. Well, we already guessed somehow that the right power would be 4 just because of a measurement of this fractal dimension that we did before. So we just compute the various quantities, and in particular, x is seen as growing like exponential minus epsilon. So you see, however you approach the critical G, you sort of approach 1 with x with the fourth root of how you approach GC. Okay, so this is again another way of saying this fractal dimension 4, because basically this is going to have to do with distances, and this is going to have to do with the number of vertices, which is the size. Okay, so now from the exact expressions I showed you before of R, we have a natural definition here, which is called the renormalized geodesic distance. Okay, all the expressions we've seen were functions of x to the n, right? So what is x to the n? It's this quantity to the power n. So you see that n and epsilon will come as a product, n times epsilon. So it's natural to give a name, if you want, to this quantity n epsilon and call it the renormalized geodesic distance. So a priori, it's a limit. You see, it's going to be a limit, epsilon going to 0 and n going to infinity, but with the product remaining fixed. Okay? So I call f of r now whatever I will get in this limit, which is this partition function. I want to call it partition function for continuous surfaces with 2 marked points at the geodesic distance. Actually, here it will be larger or equal to r for just some very simple technical reasons. And here is what it is. So it's really the limit when epsilon goes to 0 of so r minus rn, just because I want a distance larger or equal to n as opposed to smaller or equal to n. It's just a detail. And normalized in this way, divided by r, okay? And then you find out that you have to divide out by epsilon squared to find a finite limit. And that what you get just from our exact solution of before is that this f of r has actually a very nice formula. It's 3 over sinh squared of square root of 3 over 2r. Okay, so you have a sort of limiting 2-point correlation function or 2-point function for random surfaces with 2 marked points at geodesic distance larger or equal to r. Now, if you want 2 points at exact distance r, you just take a derivative, right? So this would be the one with 2 marked points at distance r. So you have an actual limit here. Okay? So I'm almost done. Don't worry. Okay, another way of getting the same result would have been to just try to extract from the recursion relation we had before its continuum limit. Okay, so you would make a certain scaling ansatz on the function Rn, and then determine how this f is constrained by this ansatz. Okay, and what you find is that f now has to satisfy a second-order differential equation. Okay, from 3-term recursion, you pass to second-order differential equation, which is sort of to be expected, but it's nonlinear. Okay, and the boundary conditions, you just translate the boundaries in n, in Rn, into boundaries in f, and you find that it has to blow at r equals 0 and to tend to 0 at r equals infinity. So if you define 1 plus f as being another function, you will find that this u here, which is equal to 1 plus f, satisfies actually what is called the Pain-Levé-1 differential equation. So finally, maybe one more probabilistic interpretation of these scaling functions would be that, well, you can get for free, if you want, from this exact solution, the probability that the distance would be less or equal to r for random surfaces with 2 marked points, right? So that would be just given by this extraction of a gn coefficient of Rn, which means just the contribution of maps with n vertices, and with at most distance at most small n between the 2 legs. Okay, so you just do whatever limits you have to do here, and this involves in particular this function u, which is solution to this Pain-Levé equation, and out of that, dividing out by whatever is needed, you will find this finite answer, which is just an integral involving this solution u to this differential equation. So this is one way, for instance, of rephrasing this exact solution in terms of probabilities or properties, if you want, for these random surfaces with marked point at geodesic distances. Okay. So very quickly, you can repeat all this with the more general case of arbitrary even valences, which we have here. Okay. So maybe I don't really do it in great detail, but well, I think the interesting part is really how you keep track of a geodesic distance in the more general case. Okay. So here I have a sort of summary of what's going on. So we have now a recursion relation again for Rn. So Rn again will be the generating function for maps with arbitrary even valent vertices with weight g2k per 2k valent vertex, okay, with 2 univalent vertices at distance at most n. Okay, that's this Rn. Okay, so now what I claim is that, again, this enumeration will be solved by saying it's 1, in the case there is no vertex hanging from there, plus a sum over the possible environment of the vertex attached to the root of a corresponding blossom tree in the blossom tree bijection. But now we have to keep track of the numbers of excess black leaves. You remember? So the claim is that this is done by a Q operator, which parallels exactly the Q operator we had in the orthogonal polynomial technique, but which will be a sort of transfer matrix which describes for you the environment of the vertex. Okay, so what can happen around that vertex? We have essentially two possibilities. We may encounter a black leaf, okay, or a descendant subtree, okay, with a certain number of excess black leaves on it. Well, the thing is that there is I can describe things with a vector space whose basis will be indexed by n being an integer. Okay, so these are just vectors in a vector space. And Q will be an operator acting on this vector space. So it's a clockwise transfer operator around the vertex, which basically, at each step, is going to tell you that either you have an extra black leaf or you have an extra blossom tree. Okay? And you have to keep track of the excess black leaves that you had. So n will be the number of excess black leaves. So if you add up one black leaf, of course, it will be n plus 1, one more. But if you have a blossom tree, because it has one loser white leaf here, it will swallow one black leaf from whatever you had before, so it will lower the number of excess black leaves by 1. So you see this operator Q, which describes the effect of turning around a vertex here, is exactly, in nature, the same operator as the operator that was describing for us the action of multiplication of an eigenvalue on the basis of orthogonal polynomials for the matrix integral. So I think this similarity in structures is very interesting. Okay, so and here is just, well, okay, what I just said in words, in pictures. Okay, I don't think this added anything. So, okay, so again, same thing. Q is viewed as a generator of steps for paths, either 1 if you go up or Rn if you go down, where n is just the height you came from. So basically, the recursion relation satisfied by Rn is exactly the same in this case and that case, except that here I have a 1, and in the other case, I have a small n over big N. So it's like writing the same equation in the vicinity of small n equals big N. It's really what it amounts to. Okay, now, same thing. This equation is integrable and exactly solvable. What's the solution? Same structure, cross ratio like this. It's the limit times the cross ratio of functions. These functions are, okay, forget about the terms here, but these occur in the integrable literature under the name of multi-soliton solutions. So basically now these are determinants, so they're a little bit more complicated than just 1 minus lambda x to the n, but not much more. And you have a bunch of x's now, not just one, but a certain number of them, which are all the solutions, actually, of the degree 2m characteristic equation, which is linearized, the linearized version of the actual recursion relation we had around its limit. So it's really exactly the same story. And so you have integration constants which are fixed, etc., etc. I should conclude here now by just mentioning the fact that in this more general case, where you don't just have tetravalent, but also hexavalent, octovalent, etc., any valences you like, the R, which is this limit, which is, I recall, was basically telling you a lot about the singularity structure of the counting function for your maps, okay? Now is a polynomial, the equation that determines R is a polynomial of degree m. So what you expect when you solve a polynomial equation of degree m is that you could have singularities which can be as bad as 1 over m, right? If you fine-tune those coefficients in such a way that many derivatives vanish, you could get a singularity as bad as 1 over m. Okay? So it means that by fine-tuning those coefficients, you can switch to different universality classes. So this 1/4 with which we seem to be stuck, right, so far, well, we can go beyond. We can really consider objects which have different universality behaviors. Okay? And here, just last thing, one sign of this different universality behavior is that you can compute the fractal dimension. It's no longer 4. It becomes 2m plus 1 in this extremal case, if you want. And then this 2-point function with distance at least r between 2 marked points in a random surface. So now you have to think of in terms of a random surface, but with special weights per vertices. So, and then take the continuum limit of that. So it's kind of a nasty object. It's even nastier than the object Gregory was talking about this morning. Then we sort of know already that if a scaling function exists, it should have this form. It should be now the log of a Wronskian of basically m solutions of a certain differential equations that you can write, etc., etc. So there is really a lot, okay, and this differential equation is actually part of a so-called KDV hierarchy of integrable differential equations. So I just leave you 3 references here if you're interested in having details. I wrote some lecture notes actually in 2004, but it appeared in 2006 on all these stories. And I think the really interesting latest paper on computing correlation functions is really about the 3-point function of planar quadrangulation. So it's now no longer 2-point, but 3-point. So you mark 3 points, and you are able to say all sorts of very interesting things about 3-point correlation functions by Boutier and Guiter, 2008. Okay. So thank you for your attention. Bon. Questions? Yes?
Okay. So if I follow well, you have 2 different approaches. One
Yes.
is matrix integrals and orthogonal polynomials, and the other one more combinatorial and blossom trees.
Okay, so I have really 2 different approaches. One is more mechanical in some sense because it uses a tool, which is this matrix integral. Now, the details, the technique itself involves these orthogonal polynomials and this multiplication by eigenvalue, and there is no real direct combinatorial interpretation for that there. Okay? Now, we change subject. We have this other approach with bijections, in which we can define sort of a very similar framework, right? With okay, it's no longer orthogonal polynomials, but it's states which are indexed by an integer. So you can think of them as polynomial of degree that integer, which tell you basically already what sort of depth you're going to end up with if you're the root, okay, when you go around your vertex. So it's a very different interpretation. Now, the 2 structures clearly are the same. They are bijectively equivalent somehow. Now, the problem is, if you think a little bit about it, the orthogonal polynomials, their real strength is not to enumerate planar maps. It's really to enumerate maps of given topology. Because this dependence on small n, for the orthogonal polynomials, we had a Rn. Okay, this small n was the degree of the orthogonal polynomials, but it actually appeared through this ratio n over n in the equation, and the large n expansion is really the topological expansion. That is, it gives you, by just picking up lower powers of n, actually, the contribution of higher genus surfaces in your expansion. So if you really want to probe deeply in high genus, you have to solve completely these equations and expand them in powers of n. Okay? Here, you're not at all interested in the same question. You're looking at planar things, but you look at one observable which you weren't able to tackle when you were doing the integral, the matrix integral. And that observable is the geodesic distance. But there is an extreme similarity in the way you're able to describe evolution in terms of geodesic distance and sort of probe higher genera. So there is really a question. I think the question is still not very well posed, but there should be a relation between probing higher genera and probing geodesic distances. Because if only because the structures of the methods that we apply look to be exactly the same. Okay? So there were a few dreams. One dream would be there would exist actually one superior matrix model, if you want, which would both allow to go in the higher genus direction and in the geodesic distance direction. Okay? But nobody has been able to make sense of that. Okay? All right. Have a question? Well, I am available for questions. Please.